Welcome to module number 4, that is Introduction to Power Flow Control, and this is the first lecture. In the previous module, just we saw that the frequency and the voltage control problems, but we did not discuss about the power flow control, and we assumed that power will flow over the lines as per minimum impedance path. In this module, just we will discuss slightly about this load curve, unit commitment, HVDC, facts already I have discussed in the previous module, and then I will discuss about some optimization techniques. Those are used in the power system analysis. So, to begin with, to power flow, just we must know that what is our load, so that we can plan our generating stations, and therefore we require the evacuation system, we require transmission system that transport power from the generating station to the load centers, and again our main criteria is that we should operate our whole system in your economic, reliable, secure and stable, along with we have to provide the better quality of the supply to our customers. Now here the correct idea of load characteristic of a particular area is very much important to meet the power requirement. You know, the load of any utility, or you can say any customer as well, it is keep on changing throughout the day. If you will see, the load is not constant and it is keep on changing. So in any particular area or in any substation, the load is keep on changing. So we must know the correct idea of the load characteristic, so that we can meet that power requirement with the minimum cost. The major portion of power generation, that's whatever the load we have, the major portion comes from your thermal, hydro, nuclear and the gas operated plants. These are also known as the conventional power plants. However, nowadays there are more emphasis to use the non-conventional energy sources like wind, biogas, solar, fuel cells and other type of energy sources like wave, tidal, etc., geothermal you can say. Presently, the combined cycle gas operated plants are becoming popular due to the several reasons, such that they are having high efficiency. Minimum erection time means easily we can construct with the minimum time. They are easily available to produce power means they can be quickly started, quickly they can go into off state, etc. Higher efficiency, if you can see, our conventional thermal power stations, the maximum efficiency is not more than 35%, and even though practically it is not more than 24 or 28%, whereas this combined cycle gas operated power plants, even though efficiency may be more than 55 to 60%. So they are double than that. So they are very, you can say, cheap, and we can reduce the cost of production. Another important concern is the location and size of different plants. Basically, they are decided based on the location is decided by where is your load, and the size is decided by what amount of the load that you are going to add into the system. So the location and the size of different plants are decided based on the requirements of load and their locations. The other factors, those are affecting the seating and sizing of generating stations, are availability of fuel, that is input energy, space, etc. The availability of fuel, for example, the input energy I am talking, it is not always fuel. It may be your even the water, that is input energy. So it is water energy, or coal energy, or gas energy, or oil energy, where they are available. What is the, if you are transporting that oil from one point to other point, or you can generate the electricity at that point and then transporting in terms of electrical energy, then always a techno-economic analysis is performed, and based on that the location, etc., are decided. Another concern, that's okay, you have decided that this generating power plant should come at a particular location, and its rating is decided based on your load curve. Again, I will discuss load curve later in this lecture. Then we require some evacuation system, and basically it is nothing but the transmission system, so that we can transmit power of generated power to the load center, or that we can connect, we can feed into the main grid system. Always we go for the more reliable system. For example, if you are having one generating stations of 100 megawatt, then we can have one line that can be rated up to 100 megawatt and it can flow the power, but always we provide the redundancy. We go for the two lines. If one line is in shutdown, then still we can operate, and we can operate our generator, and then we can feed the power to the main grid, or even though if required to the particular customer. So the evacuation system is also one of the major concern for the setting and sizing of generating stations. Now you can see the typical load. Just here I have presented very small amount of load, that is in kilowatt, at any particular substation, that is a distribution substation. Here the time in hours is starting from 0, that is midnight, to here again we are coming here to the midnight. So you can see this here, the variation is keep on changing, and sometimes it is a peak, may even occurs in the evening, may in mid. It depends upon what type of load you are using. For example, you can say if you are using your industry or commercial organization, your peak always will occur in the office hours time. But if you are using domestic, etc., if you are going for the domestic where the substation is feeding the domestic load, normally it comes in the evening time, because whenever all the lighting, fans, etc., and TV, your refrigerator, everything is on. So always a particular station, normally the complex load, mixture of the various loads are connected, and therefore we should have the load characteristic, and a characteristic that is between the time in hours for whole day. In terms of load, it is called your load curve, and since we are talking about the daily, it is 24 hours, so it is called your daily load curve. The load demand in a power system is always varying during whole day. As I already have said, the minimum capacity of generation should be such that it should meet the maximum demand. Here this maximum demand is, let's suppose 160 here, 160, you can see this is your 160. So 160 kilowatt is load. So the maximum, let's suppose it is isolated substation and it is fed by one generator. Then here you can say this is your generator, and then we are having a transmission line, and this is your load for which we have this variation. What will happen? Your maximum demand is 160, so this your generating station must be more than that 160. Why more than? Because we must go for some reserve margin in case of some transient, some disturbance, sometimes it may increase, so then it should not be collapsed, it should not be dark. So normally this maximum you can go up to 160, but it is always more than that. So here what we have to go, we may go of a generator of 200 kilowatt. No doubt we always provide here the two lines, because if one line is tripped, so we can provide the power to this load through the other one, so that we can increase the reliability or security of the system. So always the rating of that station should be this maximum that it should meet, it should be more than that. Now there is now possibility here in this, here it is possible that we can go for one unit of 200 kilowatt. Once it is decided that this will be the maximum, that's capacity of the generating units here, then we can go for one unit of 200 megawatt, 200 kilowatt, here load is only. There is a possibility that we can go for 2 into here kilowatt, or we can go for even the 4 into this. All the several possibilities are there. Now the question, which one will be the better? Now you can take the example, at certain duration here the load is even though less is equal to half of its capacity. So at this 8 a.m. in the morning, it's here the load is only 80. So what will happen? You are running one unit continuously for all 24 hours. However, at one time it is maximum loaded, and other remaining time it is half loaded or the partially loaded. If any generator is partially loaded, the efficiency will be not better. Efficiency is always when it is loaded to its full capacity. So the efficiency will be less, then what will happen? The cost of electricity generation will be more. Also another problem with one unit, that if this unit fails if there is some problem in this unit, you will not supply, you will be not able to supply even though a single mega kilowatt of the load. So it has a less reliability, and it is lightly loaded in several hours of time, so the efficiency will be less, so the cost of production will be more. But another option, that if you are going for the more unit, smaller size, certainly you will get the more reliable supply. Suppose here the 2 units you are having. If there is one problem in one of the unit, still you can feed 100 megawatt, and you can see 100 kilowatt here. You can meet up to this portion for this period, at least you can provide. So it is not completely dark. You can meet this much demand for whole 24 hours. Again, you can see if you are going for 4 unit, 1 unit is stripped, or there is some problem, then you can supply 150, and mostly you can see you can meet here only during this period. You can set few kilowatt load, and remaining you can supply. So you can say if you are going for the more and more units, your reliability of providing uninterrupted supply will be more. Then question why, whether we should go for 1 or 2 or more. If you are going for 1, then the capital cost here is less per unit kilowatt, is less compared to here for 4 units. So the cost of installed capacity will be reduced. At the same time, here the operational and maintenance cost that will be less, because you are going to maintain 4 units. Here it is only 1 unit. So maintenance cost will be also less. So always there is a compromise between whether smaller unit or larger unit, and then always we make compromise. So that those statements are written here again, that I said the minimum capacity of generators should be such that it should meet the maximum demand, but use of single unit to the supply whole load will not be practical due to economic, reliability and the efficiency reasons, as I said. Therefore, large number of units are used to fit the load curve, which is a load curve versus load demand versus the time during the day. That is called load curve. Having the lower size of units, the maintenance cost, operational cost and the capital cost increases. Hence, a compromise between selection of size and the number of generating units are made, means what size and this. So always we go for the compromise between these two. Its selection is also depends upon the cost of power, fixed and operating cost, depreciation, interest payment, etc. So there are so many factors, and always we go for the techno-economic analysis, and then we decide this is the optimal and suitable size of your generating station. So load curve is very, very important. Based on that, normally we decide the rating, and even though sometimes it is the seating also is decided by load curve. So load curve is a graphical representation of variation of load with respect to time in chronological order. Means it is from 0 hours to 24 hours it is increasing. Load curve is called daily load curve if the graph is for whole day. As I said, if your x-axis is for 24 hours, this is a whole day, so it is daily curve. If the time is 1 month, means from first day to 30th day or 31st day, then it is called monthly load curve, and so on and so forth. It is, similarly, we can go for yearly, and means for 12 months. Daily load curve for a station is not the same for all the days. It differs from day to day and season to season. So normally for the analysis purpose, we will always go for the various seasons like summer or winter or monsoon season, and based on that we go for analyzing of that one. So load curves are very useful in providing information such as the area under the load curve gives actual unit generation generated during that period. Means here, as I said, here let us suppose this is your demand, this is your time, this is your demand, and this is your load curve. So the area completely, what is this? This is demand multiplied by time. So this area gives you the total energy produced during that period here completely. Let's suppose here 0 to 24. So it will be for 1 day. If you are going for 1 month, then it is from 0 to 12 months. If you are going for 1 day, means here 30. If you are going for, this is now, it is called monthly. If you are going for yearly, then here 0 to 12 months, and then here yearly. So the area gives your total energy produced during that period. The peak here gives the maximum demand, so which I have said, and also we can calculate the other things, like here the ratio of area under the curve to the total area under the rectangular in which it contains gives the load factor of the period. Means what I want to say here, the load curve here, if this rectangular area maximum, then this area A divided by this complete area will be here, it will be giving you load factor. So load factor you must be knowing, here it is called average demand divided by maximum demand. So this average demand is nothing but the energy divided by total time. So here what we do, this energy, the total energy produced divided by the total time, here I can say is, let's suppose 24 hours. Here now this I can say the maximum demand here. Now this 24 will be coming here. So what is happening? This complete multiplied by this maximum demand. So the area under this maximum here value will be giving your the total energy maximum. So this is your energy that is produced, means area under this sided portion divided by area in this rectangular here will give your load factor on that substation. And of course this average demand is nothing but the area A divided by time will be giving your average demand. The peak of the curve gives, as I said, the maximum demand on the station during that period. The area under curve divided by number of hours gives your average demand. So this gives a lot of information. It gives your average demand, it gives your maximum demand, it gives your load factor, and also it gives the actual energy generated during that period. Here this load factor, as actually I want to remind you, you must be knowing, the load factor is totally different than the power factor. Although load and power is same, how much power? 2 kilowatt. What is load? 2 kilowatt. But the in that definition in the power system, the load factor and the power factors are totally different. Power factor is nothing but it is a cosine of angle between current and the voltage at any particular point in the AC network. However, the load factor is nothing but is the average demand divided by maximum demand. So both are different. So it is load factor, not the power factor. Another term is also defined, the loss load factor, that is another, the loss during the peak hours, means average energy loss divided by the loss during the peak hour. So this is your loss load. So various factors are used again in the, that is the economic aspects of power system that is normally discussed. Now let us come to the power flow control. Now it is decided that you are having this load, you are having the generating stations various. Now in the complete system, what happens here, let's suppose for example, I will show a simple example. Let's suppose this is your generator here, we have a transmission line here, we have another generator here, and we have here, let's suppose load, here we have the load. What will happen, this is your generator G1, this is your generator G2, and let's suppose this is your load. So let us see this example where we are having two generators and there is one load. Now the power flow. Here your, let's suppose your demand is 100 megawatt. This generator is giving 60 megawatt, and let's suppose this is providing 40 megawatt. This is not the installed capacity, it is actual generation. That's this megawatt, and this megawatt. I am talking about the megawatt power. Installed capacity may be different. Let's suppose these are having 100 megawatt, it is also having 100 megawatt, but we are generating in this fashion. So what will happen, the power will be coming here, this will be coming here, and the total here will be the 100 megawatt load we are supplying. Now, whether the current here will flow here or in this direction, we don't know, and that is decided by the impedance of these lines itself. So you don't have control because these lines are constructed. Once these lines are constructed, then if you are adding the generators, they will follow the minimum impedance, the current will follow the minimum impedance path, and it will come to the load centers, and the total is balanced, of course. Here 60 megawatt, 40 megawatt and 100 megawatt. Of course, this will be more than that, generation always more than the load, because there will be some losses in the lines. Now, let's suppose I want to control the power. As I said, we can control the frequency. How? The frequency here, as I said, this generation, if you are increasing, the frequency of the system will increase, because if load is fixed, generation is increased, frequency of the system increase. Similarly, I discussed about the voltage control in the previous module, that is module number 3. In that, we were talking about the voltage control, how we can lift the voltage by the excitation control of these generators, or we can put some capacitors here or some other devices, and then we can lift the voltage. That is a different phenomenon. Now, I want to control the power flow. Now, what are the ways? Ways are that we can reschedule these. We can reschedule these generating stations. Then let's suppose here I can say only it will be generating 50, and this will be going for 60. What will happen? Here this power will be changed, and then we are controlling. But this is not always possible. So what we do, if we are changing the scheduling, if you are having more generation in the power system, then the option is that we have to utilize those resources optimally. Why? Because this megawatt is not fixed. This megawatt is keep on changing. As I said, here the load profile of here, maybe you are going for this one, and this is, let's suppose, your 100 megawatt. So you can say only for the 1 or 2 hours it is 100 megawatt, for the remaining portion it is less. So we have to, there may be possibility when the one unit is sufficient, why we should run the second unit. So we can decide that what will be the unit should be on, which should be off. So that problem basically is known as your unit commitment problem. This unit commitment problem is nothing but it is called operational planning problem. It is related to operational. So operational, and it is sense planning. So we have to plan which unit will be on and which unit will be off. That is called commitment. Commitment means which unit will be coming at what time, which will be going down, means which will be shut off at what time. This is called your unit commitment problem. And again, for that our criteria is that we have to commit or decommit the units based on the minimum cost. Why the cost is involved in committing and decommitting? You can assume that if you are going to turn on a generating station, hydro it may be very less, the cost is of course nil because water is free, but you can assume the gas power plant, nuclear power plant, and also you can imagine about the coal power plant. Coal in the boiler it is burning for several hours without producing anything, because we are going to synchronize. We have to generate that pressure up to a certain level so that we can pass it to your turbine. So there is a huge startup cost. At the same time, there is a shutdown cost is also tremendous, because whatever the pressures are in your pipe, that will go in the air, and that energy is wasted. So there is a startup and shut-off cost is involved. So we have to optimize to meet that our load curve. We have to meet our demand at any particular station, and then we have to commit the unit accordingly. Once units are decided, then we can change the loading on that, so that again we can follow the load at that time. For example, you can say for this hour it is your 50 megawatt. It is possible that only one unit is sufficient here during this period, because 100 megawatt unit is there. So we can generate one unit, and then we can go up to this period, and then when this is exceeding, we can turn on this expensive one, and then again we can off. So we can say here generator 1 is on, generator 2 and 1 both are on, and again generator 1. So here I can say generator 1, here generator 1 and generator 2 is on, here generator 1 is again on, 2 is off. So this generator 2 is only on for this period. So it is called unit commitment. Now still you can say generator 1 is on, but it is again the loading, just how much we have to load. This is example of 2, but in actual practical power system there are more than 20 or 30 generators, even though sometimes it is count for the smaller generators, so it may be more than 100 generators, units you can say. So this unit commitment problem is very, very important, and once unit commitment problem is solved, again it is an optimization problem that we have to solve, and again that's why I will discuss about some optimization algorithms later on of this module. So once they are decided, now we have to go for the setting, this optimal setting of the committed generators, means those are on, how much we have to set their output so that we can achieve our objective. Objective may be different. For example, objective may be your minimum cost of all the thermal power generators, that is the gas, nuclear, coal, everything. Another one, we can set their reactive power in such a way that we can reduce the losses of the system. We can set these generators so that we can achieve the minimum emission level of the generator emission. We can go for the minimum control actions. So many alternatives or objective functions are possible. So if your objective is to minimize the cost, it is called economic dispatch problem or real power scheduling. If your objective is to minimize, to operate with the minimum emission level, then it is called minimum emission dispatch, where also we go for the setting of the real power outputs of the generators. You know, the thermal power station, if you are changing the output, the emission level will be the different. Emission level means emission of various hazardous gases like SO2, NOx gases, CO2, etc. So that is called your minimum emission dispatch. Another that is called optimal reactive power dispatch, means it is nothing but the real power, it is your reactive power output of these sources, and based on that we set their reactive power output in such a fashion that we can minimize the losses in the system. As you know, the voltage is very, very important factor in the minimizing the losses. So we can set the voltage and then we can achieve our minimum loss, or you can say improvement in the voltage profile, and that is called your optimal reactive power dispatch. All these objectives here, if you combined, normally in the general term they are called OPF, and it is called optimal power flow or optimal load flow, means it is your optimal load flow or power flow. Now here optimal means we are, now it is again, I will just remind you, the optimal power flow or optimal load flow are different than the load flow. In the load flow there is no minimization, no optimization, only we solve the set of power flow equations. Here we try to minimize, means in load flow the generator's outputs are fixed and then we solve it, so it is load flow. Here we change the outputs in such a fashion that we can achieve our objective, that is your whatever the objective is, and then along with the power flow equations, means your power balance equation must satisfy at each and every node of the system, means your real and reactive power balance load flow equations must satisfy at each node. So this is the difference between your optimal load flow as well as normal load flow. Here the main idea, whatever you are doing setting here, this our main idea is your energy conservation, means to save of energy, to saving of the minimum cost. The cost of water is free, of course, but the quantity of water may be limited. So normally we go for the optimal hydrothermal settling, means we have to coordinate hydro along with the thermal to meet our demand in such a fashion that the total we can meet our objective for hydro also, because the water is also used for some other purpose. It is not possible that you can discharge water continuously, because the water which is stored that may be used for your irrigation purpose. So we have to coordinate that when it is required, what will be the discharge rate, how much you are getting inside the pondage, and how we are going to plan for whole year. So it is, if you are going to combine your thermal power station along with your hydro, then it is called hydrothermal settling problem. To see the importance of this, let us, I will put one example here. For example, let us suppose we are having the two generators, means we have committed the two generators, we have decided various generators, we decided that the two generators are sufficient to meet our load. Let us suppose here the G1 is this and another is your G2, and your total load here I can say is 150 megawatt. Now the installed capacity here, let us suppose capacity, if I will write, the capacity of this is let us suppose 100 and this capacity is 150. Now, if I will say the case first, here what I can say, I am going to load these generators 50% to meet 250. So, I can say we can load 75 and we are very happy. Means again the total of G1 and G2 is equal to your load. This is based on 50%. Load 50% without any problem. Another criteria, let us suppose second, what I can do, we can load according to the capacity. According to capacity, this is 100, this is 150. So, we have to load here is 60, here we have to go for 90, and again our load demand just we are meeting. So, it is loaded according to the capacity, that is capacity is less load, here capacity is more, you can load more. Another here, let us suppose the efficiency of this is your 35% and the efficiency of this power plant is 40%. So, we can load according to the efficiency. Again our objective is to meet our load demand, that is 150, and if we are going for the efficiency, then we have to load 70 and this must be loaded 80, and again we are meeting this. You can say here 40, more loading, less efficient, less loading. Another various combination now possible. Here I can say 71, why not 79, and so on and so forth. So, there are thousands, infinite number of possibility to load these generators here and there to meet 150 megawatt. So, there is a several possibility. Again here we are meeting 150 megawatt in all the cases. Now, the question which one and why. So, this is basically called we have to adapt some criteria. Here I said different criteria are there, and then we can load them accordingly. Means here always we try to go for economic dispatch, means we have to run so that we can achieve the minimum cost. Those are the cheaper that will generate at 100% loading, and then other will be expensive, then they will be reduced. For example, you can say this is very cheap, let us suppose G1 is very cheap, so it will go for the 100 megawatt and the remaining 50 will come from the expensive generator, so that we can achieve the minimum cost generation. That is the major criteria for this. Now, as I was telling, now to see the implication, this saving, even though you are going to change the output, I can show you there are huge potential. Huge potential means we can save crores of rupees even though for small change. Even though you can go for 1% saving of this complete installed capacity that we have right now 115 gigawatt in India, even though you are going for 0.1%, if you are saving that one, then you can save the crores of rupees in which you can install another power plant. So, this is very important. You can just calculate 1% and load factor taking a something value, we can see it very easily. So, now question here, as I said that here that we have to set the generator to operate our power system economically, and then we have to have some minimum cost criteria or your minimum loss criteria, or we can go for the combination of these with some trade-off values. To control the power, always it is not feasible. Once you have decided, then in this line it is not a smooth control, and always it is not preferred. Once you have to go for optimal one, you have to fix this. Still you want to control the power. Why we want to control power? Question is that sometimes, for this example, you can always see here, there is a possibility here 60 megawatt is flowing in this line, but the rating of this line is 50 megawatt only. This line is exceeding. And why it is exceeding? Because it has the minimum impedance. So, most of the current is flowing here. So, we want to control, because we cannot operate continuously on the more than its rating, then we have to use some control mechanism so that we can redivert the power here through the other lines, and we can restrict up to the 50 megawatt here. Because more loading, more losses, and always we cannot go for more than its rating, because that will trip your line and then whole system will be in the chaos. So, here we require some control mechanism to reroute the power flow in the lines, that is called your power flow control. Here generations are fixed, load is fixed, frequency of the system is fixed, no change, but we are just redirecting the current, you can say, our power over the different lines so that we can meet our objective. So, for that various controls we have only option. We have only option that we can go for either using HVDC or FACTS controller. Already I have explained the basics of the FACTS controller, that they can control the power in any of the line or in any of the subsystem or the designated corridors. Similarly, the HVDC, they can also do the power flow control. Even though not control, it can reverse the power in the different direction here. Means power which was flowing here, it can the reverse in the other direction. So it has a potential, it has a capability to do any sort of control, and that sometimes is very, very useful. Because sometimes here, due to this overloading, suppose you don't have the control capability, you cannot load this generator up to this level. What will happen? Then you have to go further lower, and then you have to increase here, so that you should not exceed the rating of this line. And finally, what will happen? You are not meeting your minimum cost of operation, because you are going to use your expensive generator more than your cheap generator. So this resource is not utilized, which is cheaper one. So for that, to utilize the resources very properly, efficiently, we should have some power flow control mechanism, and the options are that either we use HVDC or the FACTS controllers to control the power over the line. Another option also to control the power in the line, but that is not feasible. For example, let's suppose here we have a line, we have two lines, and here is a load. What will happen? If you want to control power here in this line, you can trip this line, the power completely going here. So this is a discrete control, and this is not possible. It is not tripping one line, because purpose is not solved. We are not meeting the reliability. So the best way that we have to use the HVDC and the FACTS. About the flexible, this FACTS controllers are nothing but it is a flexible AC transmission system controllers or devices. Those are used in the power system to control the power flow, and thereby they enhance the power system performance, both static as well as the dynamic. And already we have seen for your STATCOM and SPC, we will also see few FACTS controller here in this module, like your UPFC and the TCSC, the basic controllers. Before that, what I will do, just I will discuss about the HVDC, and then we will see how this HVDC will control the power and how it is beneficial to that. To see this, let us go about the HVDC various links, then I will come to the main control schemes of HVDC and what are the application, what are the use of these HVDC links are. Now you can see the HVDC links can be categorized, can be into again three, that is your monopolar, your bipolar, and your homopolar. Name are very simple. Monopolar means pole is one. Here you can say this is your A. Means here there we are having only one overhead line, and the return path is your ground is used here. So having one conductor, and always this conductor we go for the negative one. Now question, why negative one? We know the negative conductor, suppose you are having same potential, let's suppose you are having 500 kilovolt transmission line, DC line. If you are having the positive polarity, then it will have more corona than its negative one. So we go for the negative polarity, and we can use ground as a return path. So this is called your monopolar HVDC link, because only one, mono means one, we know it very well. Here we are having one rectifier, one inverter, and then they are using, even though the direction of the current here can be changed from here to here, we can also change here by the controlling the firing angles of these two converters. Another is your bipolar. In the bipolar, again the name is bi, means two, poles are pole. Here you can say we are having pole 1 and here pole 2. There are two conductors, two poles. One pole operates at positive here and another operates at negative. During the fall in one pole, it works as a monopolar. Main problem here, if there is some problem here, the let's say fault in this line, you have to isolate the fault, you have to stop this operation of this HVDC link, and in whole the two area here, they are not transmitting power over these lines. So completely you can say chaos and the system will be unreliable. So here in this bipolar, as I said, the two poles are here. Major advantage is that, let's suppose one pole is faulted here. What we can do, we can stop the operation of this whole, this one pole, and then we can operate this bipolar into just like a monopolar, means we can have ground here and we can have return path, and then we can feed half of the power during the emergency condition here if fault is there. So it has advantage over the previous one because it was complete shutdown. Here we are able to provide 50% of the power from one area to another area, and we can control efficiently. So it has the advantage over monopolar, but the problem is that here the cost is double than the monopolar, because here you can see. Another problem here in the monopolar, if you see here we are using the ground as a return path continuously. That is very, very bad. Sometimes it may provide some corrosion to your pipelines which are passing. It may go for the interference with the other communication and other lines. So it will create a lot of problem here if we are using ground continuously as a return path. However, in this bipolar, we are not using ground as a return path continuously. We are operating in the normal period. Here you can say the current is going here and it is going like this. So it is nowhere it is passing through the ground, but only we are using ground in the emergency condition, and that we can use that. So it is better than your monopolar operation. Another is your homopolar. Here also we use two poles, but the polarity is again is of same, means here we are using the negative polarity and the other is also your negative polarity. We are using the negative polarity again to have the minimum corona loss, because in high voltage transmission lines, whether it is AC or DC, we are having corona loss. No doubt the corona loss in AC system is very, very high compared to your DC system, because it is a frequency dependent loss. So your corona loss, that is a P, is proportional to F plus 25. If your F is 0 in DC, so it is again it is a minimum in the DC. So two or more conductors having same polarity here, two conductors I have shown, and then we are having the homopolar. Normally negative polarities are used due to the less corona and radio interference. Here another problem is that every time we are using ground as return, you can say this current will be flowing here like this. This current is flowing like this. Now you can see this ground, every time you are using the ground as a return path, and that is not good for basically the safety purpose. So during fault here, advantage over the monopolar is that in monopolar also the ground was used as a return path. Here again, if there is a fault in one system, then we can operate into the monopolar operation, and then we can feed the power to other area and we can control this. Now let us go for the basic principal part of your HVDC system. Now I will show this figure. First see this. That is the components of HVDC transmission here. Here you can see, just I have not shown, it is a bipolar. Normally let us take it is your plus, here it is minus, and normally the bipolar, the voltage is written as a plus minus voltage of one pole. Let's suppose I have written 500 kV. It shows that here it is your 500 kV with respect to ground, and here it is also 500 kV with the negative sign. So plus minus is shown for your bipolar operation, means automatically if you are using plus minus means it is a bipolar, means one is positive, another is negative with respect to ground. So the total voltage difference between these two lines is 1000 kilovolt, and we have one line that is from Rihan to Darri. It is a plus minus 500 kV line and feeding 1500 megawatt power. So the major components in HVDC transmission system, one is your, that is your, here you can say converter. These are the converters. Here this is a converter, this is your converter, this is converter. Here converter can be used as a rectifier, can be used as inverter, but converter is a global name for both rectification and the inversion operation. We require the transmission lines. These are the transmission lines. We require the smoothing reactors. Here this is a smoothing reactors, you can see. Why smoothing reactors? Because we want to have a smooth DC current over these lines, because here due to the firing the current will keep on changing. So normally here the current variation is there, but we can use a reactor so that current will be perfect DC. We are using here the transformers. These are the transformers. It is also transformer, and these are called converter transformer, because these transformers are in design different than your normal conventional transformer, because I will see that this transformer is highly stressed, because here the DC current is flowing. Sometimes these windings are highly stressed, so that saturation may take place. So we have to go for all these. We also use some filters. We require the filters to filter out the harmonics, because these converters will inject harmonics into the system. So we have to use the filter to filter out the harmonics, means only we allow the fundamental components from the system. And also other sort of, you can say, lightning arresters, grounding, because here the grounding part is there, you should have a grounding rods, etc. So all these are the major parts of your HVDC transmission system. So let us go back. First is converter, and the converter is the main part, that is heart of any HVDC system. It is very expensive device because we use the power electronics devices, and also due to the huge power rating there will be excessive loss and in converter devices, so we have to cool them properly, and the mal-operation, or you can say any problem in the converter station, that will lead to the complete shutdown of that link. So it is very, very carefully and operated properly. So each HVDC line has at least 2 converter, one at each end. As I said, here let's suppose this is one line, DC line is there, so we must have one converter here, we must have converter one at least here, and then here the 3-phase AC supply and the converter here. So we must require at least 2 converter, both have station at the both end of the transmission line. Sending end converter works at here, let's suppose power is flowing from here, then it is said this is your rectifier and another is you call your inverter as usual. So this sending end here, the power is flowing from this end to here, that is from A to B. So this is called your rectifier, and it converts from here AC to your DC. Here is a DC, and however at the receiving end it converts from DC to AC, and it is called inverter operation. Now we know that, even though in the fact devices, when I was talking about the various devices, I said that we are having the one single thyristor unit of this 8 kilovolt we are expecting, and we are having this kiloampere of rating. But I said a HVDC link here, let's suppose plus minus 500 kV. So current may be in the kiloampere, several even though mega ampere. So what we normally do, we go for various addition of the thyristors. We have to add in series to provide the proper voltage level, and also we have to go for the parallel combination to provide the complete current rating of the link. So the several thyristors are connected in series and are parallel to form a valve. Now whatever I showed here before, here if I write here in this box, this is your the converter circuit, and that converters we are using in different legs. Normally the bridge converters are used. Again, it has a several advantage over the other configurations. So in one leg, one limb, there will be several series thyristors, and also we provide some safety factors. Suppose required, here we are having 10 kilovolt thyristor, and our required in one leg it is 500, then it is not 50, we can go for the 60, 70, because if one thyristor fails or punctures, we should not take it out, we should only take out when maintenance is taking place. So we have to go for some safety and redundancy in this. So we have to go for series and the parallel addition of these valves, and that here calls one valve. You normally know the bridge converters here. Normally if you are having this is your bridge converter, or you can say bridge rectifier, that is the 3 phases. So we are having, this looks here the 3 upper and lower, 1, 3, 5 numbers, I can say 4, 6, 2. Here, even though 1 here I have shown one thyristor, but it is not one thyristor, it is called one valve. Valve means it is addition of several thyristors in series as well as the parallel to make its proper rating in the voltage and the current. So bridge converters, as I said, are used for HVDC application. This is a bridge converter. We are using here thyristor valves, and then it is your rectifier, and inverter end also we use the bridge converter. Again, it is a 6 pulse or 12 pulse, again required, depends upon what is your power rating, what is your harmonics filter, etc. So it is decided based on that. So the current rating of converter stations can be increased by putting valve in parallel, means we can have the 2 valves here. This is, let's suppose, valve. We can have the 2 valves in parallel. So this is a parallel, and then we can increase. there is a possibility that we can use the thyristors in parallel, means one thyristor here, one thyristor here, and we can use several, and then it is one valve. So in one valve we can use several parallel, and other valves may be in the parallel, and again even though sometimes bridges are in the parallel, means 6 here in one bridge, so we can have the 2 bridge inverters parallel to increase the current rating. Sometimes you can say combination of all these 3 is also possible. So for the current rating enhancement we have to go for parallel connection. For the voltage rating of the converter station can be enhanced or increased by the valves in series, bridges in series, or thyristors in series, and the combination of above. Means for here you can say this is your valve, we can have various thyristors here. So this is one, you can say valve where we can add several thyristors, or we can have this is various bridges, they are connected here in the series to increase this. We can also add the bridges, and again we go for the 12 pulse operation, basically we add this to increase the pulse number. The main requirement of valves are to allow current flow with the low voltage drop, means main requirement of valve whatever you are using here, that it will allow the current flow with the minimum voltage drop. Here the voltage drop must be minimum across during the conduction period, and it should offer the high resistance during the non-conducting phase or blocking phase. So when it is on, it's just like a short circuit, when it is off, just like open circuit. So it should be ideal switch characteristic we want. But since ideally it is not possible, so when it is on, it will offer very you can say on is very less. When it is off, so R off, it is practically very high. It is not infinite. It should also withstand the high peak inverse voltage during the non-conducting phase. Once this bridge is not conducting voltage is 0 across this, almost 0, because R on is very less. Once it is not conducting, the voltage across this, we can see the huge voltage is appearing across this valve, and then it must withstand that peak high inverse voltage during the non-conducting, because the inverse voltage is appearing across that, and there may be some possibility if it is not withstanding, it may puncture and it will get short circuit and damage. So that creates another problem. So this is another requirement for this. Another requirement to allow a reasonable short commutation margin angle during the inverter operation. Now what is this? Normally what we do, if you remember, for any this here, this is sinusoidal. If the voltage across any thyristor is going to appear positive, what we can do, we can here alpha is 0, we can turn on at any period here during this period, that is 0 to pi. If you are just turning before here pi by 2, this will give you positive voltage. If you are turning on just after this, it will give you negative voltage. So the inverter operation, normally we try to just see the advance angle here, and we fire here, that is alpha should be more than 90 degree. For rectifier operation, this should be less than 90. So what happens once this is off, because before that it must be off, otherwise the negative polarity will appear, and thus it may again start conducting. So it should have some margin, just we should have, that is called commutation margin angle during the inverter operation. That is, inverter operation is very complex and tedious operation than the rectifier operation, because there is no mal operation, very less possibility of mal operation. However, in inverter there are a lot of mal operations and malfunctions, and in that if it is mal operating, lot of harmonics, voltage distortion, everything will be arising there. So we should be very careful there. Another requirement, that is smooth control of conduction or non-conducting phases, means from one to another, because always we use the bridge converter. As I said, here it is a bridge converter. From 1 to, let's suppose 1, 3, 5, here shifting from 1 to 3, it should be smooth, it should not be jump, otherwise there will be some transient, etc. Normally 6 pulse operation is adopted in HVDC system, but sometimes 12 pulse is also used. Again, what do you mean by pulses? Pulses means in one AC cycle here, let's suppose this is your AC cycle, your DC voltage here, I can say here it is, if it is 6 pulses, it is called 6 pulse. If you are go for the 12 pulses, what will happen? Here, now you can see 12 pulses. So this is a more smoother and less harmonics. Here it is more harmonics. So we can go for the 12 pulse, and then harmonic contents required is very less, because always the harmonic contents which are entering in the AC system, it is NP plus minus 1. What is that? P is number of pulses, N is 1, 2, 3. So what will happen if it is 1? Then let's suppose for 6 pulse, here we are getting 5, 7, and it is 11 and 13 harmonics. If we are using 12 pulse, what is happening? We are having 11 and 13 and so on and so forth. So we are not having these harmonics automatically eliminated. Otherwise, we have to go for the filters for 5th and 7th harmonics along with 13th and 11th. Here only we require the harmonic filtering scheme for 11th and 13th scheme. So this converter operation is very, as I said, very important, and it must withstand its reverse voltage. It should have the inverter operation should have the commutation margin angle sufficient, and it should operate just like an ideal switch, and the conduction from one to another switchover should also very smooth. Here the number of again 12 pulse, if you are going, it is not possible to go for more pulses because the transformer connection will be the different. The beauty of here one system, I will tell you what happens. Normally if you are using 3-phase here, 3-phase supply system here, and then you are having a bridge converter here. For example, here this is one bridge converter, here we are having another bridge converter. Normally this is, let's suppose, star star. Here if you are having a star delta connection, then already there is a phase shift of 30 degree, and you are adding the voltage. Means 2 6 pulse converters, if where they are connected by here star star and star delta, and if you are adding the voltage, automatically they will provide the 12 pulse in that one. For example, I will show you here. Let's suppose here we are having here the voltage, let's suppose the 12. I am talking only 3, and then we can see we are having this. What will happen if you add? You will get this 6. So similarly, you can go for this one positive cycle I am talking, and then remaining here. So what will happen here? Automatically the 2 6 pulse converter with connected, because we have the inherent property of this 3-phase connection, 30 degree lead. So here it was the in 360, earlier it was 60 60. Now we have shifted 30 degree and 60 60. So in 360 we are having 12 pulse operation, and then the same transformer 3-phase is very good for using the 12 pulse, and normally we go for the 12 pulse operation rather than using 6 pulse to 6 pulse bridge converters. So this converter operation and its analysis, its performance is very important, and we will see if we will have a time, then we will discuss about that one as well. Another is your, as I said, the converter transformer. That converter transformer, for the 6 pulse converter, a conventional 3-phase or 3 single phase transformer is used. Means we can use the 3-phase, or we can use the single 3-phase transformer for 6 pulse converter. However, for the 12 pulse, as I said, configuration, the following the transformers can be used. We can use the 6 single 2-phase transformer. 2-phase 6 means 12 phases we can give. We can use the 3 single phase transformer with the 3 windings, or we can use 2 3-phase binding. Normally this is used. In converter transformer, it is not possible to use binding close to yoke, since potential of its winding connection is determined by the conducting wall. If you are using to vary yoke, what will happen? The voltage sometimes difference is very high, and there is some insulation failure. So the converter transformer is not possible to use the winding close to yoke due to the potential problem. Hence, entire winding is completely insulated. Complete binding should be insulated, because due to the huge potential difference. As the leakage flux of a converter transformer contains very high harmonics content, it produces great eddy current loss and hot spot in the transformer tank. Because there is a huge leakage flux, as I said, the sometimes voltage is very high, and also is a sudden DC fluxes. It is not a smooth. Here, for example, the voltage which is appearing in the normal transformer this, but here the possibility that voltage here will be and current will be like this. It is not a perfect, although it is, we can go for this. So it is a huge surges, and also sometimes the DC will be appearing in the mal operation. Sometimes it is a dead short circuit in the DC circuit. So that is appearing, huge current will be flowing the transformer. So the transformer must be capable of that one. So since the fault current due to the fault across the wall is predominantly controlled by the transformer impedance, the leakage impedance of converter transformer is higher than the conventional transformer. As I said, during your short circuit or sometimes mal operation, when your U is more than that, here there is a short circuit, and then we only the option that we have the leakage impedance. Here in the case of 12 pulse configuration, if 2 3-phase transformer are used, one will have a star star, another will have star delta. Already I explained, because we have the inherently 30-degree phase shift that we can achieve the 12 pulse by adding 2 6-pulse bridge converter. Online tap changing is used to control the voltage and the reactive power control. We use the online tap changing transformer to control the voltage. So we saw in this lecture number 1 that the various components of HVDC. Also we saw the load curve. Here I explained the converter as well as the converter transformer. Those are very, very important components of the HVDC link. In the next lecture, we will see the various other components like the smoothing reactors, we will see the filters, and then we will again go for the various control mechanisms in the HVDC link. Thank you.